Okay.
Well, hello everyone. Thank you for joining this week's seminar. We have the great pleasure of having with us Silvia Manconi. Silvia is a junior professor at Sorbonne University in the Laboratory of Theoretical High Energy Physics, in Paris. She graduated in 2019 from the University of Turin, after which she had a few postdoc positions in the Institute of Theoretical Particle Physics and Cosmology in Aachen. She was a Marie Curie Fellow at the laboratory that I'm not able to pronounce the French name of, but it's in France, in Annecy. But please, Sylvia, tell us after. And she's very much interested in astroparticle physics and in specifically in indirect dark matter searches, and works on various models of galactic phenomena producing gamma rays and cosmic rays. So thank you very much, Sylvia, and please take it away.
Thank you. Thank you for the nice introduction and for the opportunity to present my work to your seminars. So I would like to tell you about a topic I've been working on a lot in the past few years that has been really a hot topic in the astroparticle community, which is the inner galaxy seen in gamma rays. And the reason why this is interesting is that, as I will tell you in the progress of the talk, we see something that we were possibly expecting that might be exciting, might be a new discovery, both in new physics, but also in astrophysics. And the understanding of the origin of the so-called gamma ray galactic center excess, the topic of this talk, has been keeping busy many of the researchers of my community. So if you are very busy and you need to detach from the online seminar, I know that sometimes might be very difficult to follow. I will do my best to keep you engaged, but I like to start the talk directly with my take-home messages. So in short, what I'm going to speak about to you today is that while searching for indirect dark matter signals, we found an excess of GV gamma rays at the Milky Way center. And the interpretation is debated. So depending on the person that is giving this talk, possibly you will get a different opinion, but results and data are data. So I'm trying to be unbiased on this. And recent results support that this excess is coming from new astrophysical phenomena. And for the future, complementary multi-wavelength and messenger probes will likely help us deciphering this excess, as many other challenging topics in our fields of astrophysics and theoretical astroparticle physics. So the outline of the rest of the talk, if you are willing to follow me, is the following. I'm going to give you an introduction, and knowing that I was talking mostly to an astrophysics laboratory, I decided to center my introduction on the topics that are specific or indirect dark matter searches. Then I will give a bit of the status of the interpretation of this excess. I will give some selected results, mostly taken by my own research. And then if time will be nice, I will also give you an outlook. So I just insert this slide to remind ourselves that in order to explain the observed distribution and amount of structure in the universe, we need a dark matter component in the universe energy budget. And this is coming as an evidence, gravitational evidence only so far, at different scales in the galaxy. The scale that will be most important for us is the galaxy scale, so kiloparsec scale, in which we see this happening in our own galaxy, but also in external galaxy, as this was discovered in the dynamics of the rotation curves of spiral galaxies. So according to those results, galaxies are embedded in dark matter halos, which follow this radial profile, and also the Milky Way. And those gravitational couplings, those gravitational probes that give us the evidence just probe the total mass and the spatial distribution, but they don't give us much of a definitive answer of what is the nature of dark matter. And so in order to understand the nature of dark matter, we have been working in the past decades trying to come with different theories. And different theories are, let's say, divided with many different assumptions in this theory landscape that I decided to show you. We have a nice summary of the different hypotheses that we have at the moment for the nature of dark matter. Dark matter can be a new particle that, depending on the mass, can then behave as a particle or as a wave, can be a macroscopic object, or can be something else. For example, we are still missing some ingredients in our description of gravity. And in this forest of theory landscapes, we search for well-motivated theories to test with observational data. This is the job of phenomenologists. And whenever you ask to what is well-motivated can change, for me, I think that well-motivated means that theory models for dark matter are predicted and prototypical in the sense that while testing one, we can also test other ones. They might be solving other issues that we have in our current understanding of the nature, or can be simple and elegant on a theoretical point of view. So for indirect searches, which is the topic of the talk, we use nature-made experimental setups at different redshifts. So I'm going to use mostly our galaxy for that, in which we search for annihilations of dark matter. For example, if dark matter is a particle, you see here a possible scheme of the interaction in which standard model astroparticles are produced, or subsequent effects are produced. For example, the heating, ionization of the change of the structure, formation, and evolution of some astrophysical objects. So we are here in our solar system. We assume that the galaxy is embedded in a dark matter halo. Those interactions occur, they produce particles, and our aim is to detect those particles and trying to understand in an indirect way what are the properties of dark matter. So in this sense, we use the universe as laboratory, but we have the baryonic universe as background. Many interactions, as I will show you, and the Galactic Center Access is a textbook example of this, actually mimic what are the signatures that we are searching for in indirect searches. So in order to search for the signals, we can follow different strategies. So we can integrate large masses in which we expect to have more dark matter. For example, we can look to the center of the galaxy or to galaxy clusters. We can integrate the effect of dark matter into large distances and timescales using cosmological probes, for example, the cosmic microwave background. We can, and we are, exploiting the precision of astrophysics measurements, for example, coming from the measurements of cosmic rays at different energy scales and of photons at different energies. Or we can try to search for systems in a universe in which we believe that dark matter is dominating them, and the signal to background then is pretty high. This can happen, for example, in what we call dwarf satellite galaxies of the Milky Way. But the priority that we usually assume as a majority in our community is, from a theoretical point of view, is that our theories are predicted and prototypical. So by searching for a signature, we're actually testing a big landscape of possible theories for dark matter. And of course, we have the observational bias that we can actually test those models with the current data that we have. And here I've been underlying three dark matter candidates that have been discussed and tested a lot in the past decades, which are weakly interacting massive particles, so possible new particles that arise at the weak scale with GeV masses, axions that are coming in some solutions to other problems of the standard model of particle physics and behave as a wave because they are not very massive, and the possibility that dark matter is made by new macroscopic objects that are primordial black holes that needs to be primordial and not only black hole, because we need them to explain the structure and evolution of the universe at different redshifts. You can also have another bias nowadays by searching for dark matter. You can have the anomaly bias. So we have different anomalies in the observation of particle physics experiments. astrophysics, and many other observations, in which we have been finding hints of what we have been looking for. And in this nice plot that was compiled in this recent review of dark matter, you see that we have different anomalies, both in different experiments. Here you can recognize the name of some experiments, the same as some excess that you might have heard about. And those 4 lines are what, according to the author, this is the most likely origin of those excesses. They are possibly coming from astrophysics, they are possibly going from background mismodeling, some experimental mismodeling, also theory problem. And new physics is understandable. So for example, for dark matter, we will like to be closer to the new physics, according to this personal bias of the author of this review. And what I'm going to talk about you today is the GV excess that, according to this review, is one of the closest one to new physics, which means new physics or new astrophysics for us. So let's have a closer look to what are the indirect signatures of these weakly interactive massive particles. So we have a mechanism to produce the particles that we call the thermal freeze-out, in which new massive stable weakly interacting massive particles with GV-TV scale are naturally produced and become relic of the initial evolution of the universe. And in order to match the abundance of dark matter that we observe today, what we find is that we need an annihilation cross-section, which is averaged on velocity, which is of the order of the weak scale, this value that I'm going to show you also afterwards. So I told you before that with indirect searches, we search for annihilation in the case that will produce extra fluxes of what we call astroparticles. We are going to concentrate on photons. And in astrophysics, what we typically expect in indirect dark matter searches is that if you are looking to the flux of a source, our galaxy, our diffuse process, most of the astrophysical processes, to a first approximation, will go down as power laws, while from dark matter annihilations, we expect a bump-like feature in the fluxes that is coming from different processes. For example, line emission, in which case this is going to be very concentrated in a specific energies, prompt emission, secondary emission, or even particles. And the properties of this possible bump, this signature that we expect in the astroparticle fluxes, is directly correlated to the particle physics nature of our dark matter candidate. Specifically, the normalization is connected to interaction strength and to the dark matter mass. Then we have a proportionality on the specific annihilation channel that we're looking to. And then, since we are looking to annihilation, we need to integrate along the line of sight what is the dark matter density square of particles that can annihilate. And as I told you, for the specific candidate that we consider well motivated and testable, we have the prediction that we expect signals at the GVTV scale. And the experiments in which nowadays with astroparticle physics, we have been searching the most for indirect signals of weakly interacting massive particles is the Fermi Large Area Telescope. This is a gamma ray telescope that is a full sky survey that is taking data from few MeV up to hundreds of GeV. And nowadays has been releasing more than 15 years of publicly available data. So even for people like me that they don't work directly on the experimental collaborations, we have access to the observation of gamma rays of the full sky in this energy range. And this is a statistics that was never reached before with such angular and energy resolution. So in the data of this telescope that you can see in this map, this is a counts map in which you can see the counts of gamma rays with energies larger than 1 GeV that has been collected after 5 years of data in this specific example. In this counts map, since the first year of data, an excess of gamma rays towards the inner galaxy, and I'm going to describe better what we mean with the inner galaxy, but let's think about a square 20 by 20 around the galactic center, an excess with respect to what I'm going to tell you in a moment has been found. This is statistically significant. It's not depending on the specific analysis of the sky that you do. So it's not an experimental issue, and is making up a few percent of the flux of the inner galaxy. And it has been investigated by many different complementary collaborations and researches in the past years. I was telling you, but we tell excess with respect to what? So in this counts map, we see that where we see more photons, colors are more to the yellow. Where we see less and less photons, we go to red to blue. And we see that, I mean, the excess is not possible to be seen at very high, but since I told you that it's few percent, but we detect this as an excess with respect to our modeling of the diffuse emission of the galaxy, plus the detected sources that we collect in the catalog. Specifically, these structures, diffuse structures that we see along the galactic plane are coming from what we call the galactic diffuse emission that is produced by cosmic rays interactions with gas and radiation fields through different processes. For example, Brech-Strahlung and Pine decay, which are correlated directly to the gas structure into the Milky Way, or inverse Compton scattering, which is mostly correlated to the interstellar radiation fields in our galaxy. Then apart from this diffuse like emission, you see that we have also individual detected sources. Those are collected into catalogs. And then we have also large-scale structure features, for example, the Fermi bubbles or structures that are correlated to structures in other wavelengths, for example, the loop one. And just to have a closer look to what we mean with astrophysical backgrounds, this, as I told you, is the diffuse emission from cosmic rays, which mostly produce energy losses, photons through energy losses. For example, let's focus on the Brech-Strahlung. We might have protons in cosmic rays, which, according to what we see locally, they produce the majority of the flux of cosmic rays. They might interact with protons into the stellar medium, produce pions that will further decay into photons. And the target to this is going to be the gas density in the Milky Way. So we have models to describe those phenomena that are obtained with cosmic ray propagations in the galaxy. So we solve equations like this, both numerically and analytically. And then in order to compute what is the expected gamma ray flux, so what you see in those templates maps, we do the integral along the line of sight, taking into account, for example, this is the example for the inverse Compton, what is the density of electrons along the line of sight and what is the power of emission of the different processes. And this part of the modeling of the gamma ray sky is having a per se interest in high energy astrophysics. So this is also important for how aims in studying the excess. And the other source of background are sources that are particle acceleration sites. So also here, there is a per se interest in high energy astrophysics because understanding better the backgrounds, for example, the emission in sources such as pulsars and millisecond pulsars, we can understand better the acceleration processes of sources in our galaxy and possibly beyond. So what are the current leading interpretation of this excess? There are at least two, and they are debated. So in this sketch, what I'm representing is now a sketch of the Milky Way. So we have the spirals. We are here with our Fermi telescopes. The sources are mostly distributed in the disk of the Milky Way, while if we have a dark matter halo, we expect this to be more concentrated and have a higher density towards the inner part, towards the galactic center, but having also a distribution along other regions. So we are here looking towards the galactic center, and we are integrate all the possible photon sources that we have along the line of sight. So will not come as a surprise if I tell you that one of the main interpretation of the galactic center excess is actually that we are seeing a first indirect evidence for dark matter annihilation into the galactic halo. I'm going to explain to you why the characteristics of the excess actually match our expectations for this. On the other hand, we have been possibly missing a new population of sources that might reside in the galactic bulge of the Milky Way. And so the second interpretation of the galactic center excess is the stellar hypothesis, that we have a new population of very faint sources that are coming up for the first time in gamma rays as a glow of photons into the GV. And we call them millisecond pulsar likes because of what I'm going to tell you in a moment. So in this map, I'm going to show you what will be the theory stream. Other matter-only sky, we know backgrounds from standard astrophysics, and here is just to corroborate the fact that indeed the galactic center will be the best target to look for dark matter indirect signals, because it's where you expect the higher dark matter signal. But we saw before that the center of our galaxy and also the galactic plane is very busy with astrophysical processes, and is also the region in which we expect the highest background. Here is just to remind what is the photon flux that is coming from the matter annihilation, and the fact that we expect GV gamma rays from those specific dark matter candidates. But what are the other hypotheses? When I tell you stellar hypothesis for the galactic center excess, what I mean? Specifically, we believe that a new population of millisecond pulsars might be residing in the galactic bulge. And millisecond pulsars are specific class of pulsars in which we have evidences that particles are extracted from the star surface and are accelerated in the pulsar and possibly also in the surrounding, producing gamma rays. And our goal is to try to understand how photons are produced in those pulsars and millisecond pulsars, and try to understand if they can mimic or not what we see into the inner galaxy. So for the sources in the galactic disk, we see a pulsed plus stable extended emission. This is only for the pulsars, actually, and this is what we call pulsar halo or TV halo. This is another topic I've been working on in the past few years. We have a mechanism to explain how the spin-down luminosity of pulsars is translated into particles and electromagnetic energy, which is the spin-down decay. And we observe for sources that are in the galactic disk an emission coming from radio to GV gamma rays that is coming from the synchrotron and inverse compton energy losses of those electrons and positron pairs. Specifically, millisecond pulsars are good candidates to explain the galactic center excess because they come from old, possible recycled binary pulsars, and we know that at the galactic center, indeed, the population of all stars is very numerous. The point here is that with the galactic center excess, we might be seeing a new population with specific and peculiar characteristics that is just happening to reside at the galactic center and is not part of the population that we see in the galactic disk at different wavelengths. And by the way, pulsars specifically, so younger objects, not millisecond pulsars, have been found guilty for another excess that has been keeping busy the community in astroparticle physics, the positron excess in local cosmic rays, a topic I've been also working on. So now let's have a look to the different properties of the excess and if the two hypotheses can match or not the expectations. So what about the intensity, the normalization of the signal? We saw before in the equation that I reported here that the dark matter flux is indeed proportional to the annihilation cross-section. So what happens if I now put the annihilation cross-section that serves me to explain the dark matter density today, to normalize this signal? Actually, this is fitting pretty well for a dark matter mass that is between 10 and 100 GeV. And let me explain this plot. So here you see the annihilation cross-section, and here you see the dark matter mass. And those different regions are regions that at the time they were fitting the galactic center excess with very good accuracy. This means that with a thermal Rayleigh cross-section that is around here, we can indeed explain for quite some channels of annihilation pretty well the intensity of the galactic center excess. And there are many more specific theories explored. I didn't recompile the tech here, I see, but here I just inserted before the talk 2 recent works in which they've been exploring specific realizations of dark matter theories to explain the excess. What about the millisecond pulsar side? So in order to normalize the signal here, we need a luminosity function. We need to understand how these possible sources emit photons. And as you can imagine, and this is a problem that we share in different parts of astrophysics, this luminosity function can have different shapes as a function of the luminosity here shown in erg per second, because we might be having few sources that are very luminous to match the normalization, but we can also have a lot more sources that are less luminous and so have luminosity functions that are more shifted towards low luminosities. So it's for sure clear that observer sources in the catalogs are not enough to explain the excess. And the modeling of this new population is very debated. So in this forest of lines, you see a selection of possible luminosity function models that have been proposed in order to explain the excess. So we still don't have agreement of what will be the best luminosity function here. One possibility is that you assume that the luminosity function of this population is the same as the disk population of millisecond pulsar. You can also look to globular clusters. There are different options, and this is debated. In general, in order to reconstruct the sex properties, there have been a significant community effort developing new models and methods and tackling bias from background mismodeling. So the main properties that we want to reconstruct, apart from what I've been describing to you, are also the energy spectrum, the morphology, and the photon statistics. And what I'm going to speak a moment about, because this is a good introduction for what I'm going to discuss to you connected to my work, is the morphology. So in the case of dark matter, at least the best of our knowledge of current cosmological simulation predict that dark matter densities in galaxies should be almost spherically symmetric, at least at the scale of 20 by 20 degrees around the galactic center. And so we expect that the dark matter signal will be, if it's coming from the excess, roughly spherical symmetric. While if we assume that this is rather coming from stars in the bulge of the Milky Way, we expect this to be following the same distribution of all stars into the galactic bulge. And so we expect a more bulge, boxy shape around the galactic center. And as a matter of fact, there have been a lot of debate into the reconstructed morphology of the excess, but I can report that with recent systematic comparison, the stellar model, so this morphology, is preferred to describe the data. And another important characteristic is the energy spectrum. And here comes the first time I show into you actually what is the energy spectrum of this excess. Those are old points taken into from a review from 2020. And you see that this is the spectrum extracted of the galactic center excess is peaked a few GeV. And here the different lines you don't need to read, but one of those is dark matter annihilation, and the other ones are the spectrum from millisecond pulsars, for example, that we have in the disk. So you see that we cannot really disentangle this, at least look into the peak of the galactic center excess. But what about looking to the full spectrum and specifically putting the spectrum, this is a much more recent reconstruction of the excess spectrum, and looking this into the linear scale to try to underline the high energies. It happens that most dark matter models can explain the bulk of the excess at few GeV, but fail to explain this high energy tail. While if you combine the prompt emission plus the inverse Compton energy losses of electrons and positron pairs into those millisecond pulsars, which are those two lines that you see here, this is the prompt and this is the inverse Compton, you can actually match pretty well the high energy tail that has been detected for the galactic center excess. So this observation is offering a crucial discrimination power because it's naturally explained in the stellar hypothesis, while dark matter will need more tuning. And a final characteristics is what I call the statistics of the photon counts. So if we have a diffuse-like emission coming from dark matter annihilation, we would expect the excess to be, at some point, be resolved as a truly diffuse emission. While if we have point sources and imagine that you have an infinite resolution for your detector, you will be able to see them individually. At the moment, we cannot because they appear as a faint, unresolved, we call sources. But still in those two options, you might be still seeing a difference in the statistic of the photon counts. And what we call photon count statistics methods that are made to measure the collective properties of faint sources have been developed in order to extract the properties of these photon counts in the region of the galactic center excess. So there have been many different implementations. I've been leading one of the two since my PhD. So this was a very brief recap. Is not needed. I just want to recap the current debate. So from one side, we have the mystical pulsar hypothesis. From the other side, the dark matter hypothesis. But here, our debate is based on the fact that we understand the characteristics that are reconstructed from the data of the excess, so the spectrum, the morphology, and the photostatistics. But in this game, what can happen is that if our interstellar diffuse emission is not modeled correctly, we might end up reconstructing the properties of the excess wrongly and giving worst and not accurate interpretation of the excess characteristics. So what I mean with mismodeling is that whenever you have a model and you fit it to the Fermi-Lat data and you do it with standard template fitting, you will end up with residuals in the sky that are very structures, and they can go up to 4 sigma in the sky. And this is really independent of the specific paper that you take. And this can be up to 30%. And the mismodeling at low angular scales is specifically the one that can be more dangerous because can give to you spurious evidence for new components, such as, for example, point sources. So can participate to your interpretation of the galactic center excess as point sources. We have now developed some different methods to cure diffuse emission mismodeling. And this is what I'm going to explain to you with my current contribution to the topic in the 10 minutes that I have left. So what you can do is, of course, let's go to the long term. You can improve your galaxy model aiming at having true 3D gas distributions, photon fields, or having better models of your cosmic ray distribution. But this is a long-term achievement, and different groups are working on this. But in the meantime, the strategy that we are following as a community is to develop data-driven fitting models that account for the intrinsic uncertainties. So we kind of put into the statistics the unknowns, and we try to produce models that are regularized and can reduce the residuals at low angular scales. So we basically go from this to this, so having much less residuals in the region of interest by introducing a very large number of parameters. And to regularize this fit, we introduce physics-based regularizations and priors. So for example, if you have the inverse Compton scattering process and you know what is the spectral shape of the inverse Compton scattering from the physics, your modulation of the initial template cannot go beyond what you expect from the physics, but can be still kind of marginalized over the uncertainties that you have, for example, in your photon fields. So far, this is the summary of what I've been a bit reviewing. We have an excess that detected a FUGV towards the inner galaxy in the Fermi-Lat data. The origin is debated, and we've seen that the center of our galaxy is gamma ray busy. So we might be having dark matter, pulsars, and cosmic rays. So reconstructing the characteristics of this excess is really challenging. So in the final part of the material I would like to show you, I'm going to introduce to you a work that I've been recently done in collaboration with Francesca Calore and Fiorenza Donato here, in which we have been trying to focus on the high energy tail. So I show to you that we expect that if there is a high energy tail in the galactic center excess, this should come mostly from the stellar interpretation. So we have been trying to access the characteristics of the excess just looking to energies larger than 10 GeV in Fermi-Lat data, using two different techniques and building a model for the gamma ray sky, combining the adaptive background models that I showed to you before that can minimize diffuse emission systematics, and using those methods of photon count statistics that can measure faint and point sources, but after reducing residuals. I'm going to skip a bit the technical details of the two methods because of time, but I'm happy to discuss about this in the question time. I'm going to jump directly to the results summary. in which by analyzing the region 20 by 20 around the galactic center in Fermilab data for energy larger than 10 GeV only, what we find in this paper that is accepted by PRD is that an excess is found also when you look only to 10 GeV and larger energies. So this means that we can tell that there is an excess into the inner galaxy also at high energies only. We find that the morphology of the excess that is measured from 10 GeV energies above is also found to be better explained by a stellar-like distribution compared to a spherically symmetric dark matter. And finally, a population of fine point sources is relieved with density that are higher with respect to other sky regions. And this is a bit the results of the source count distribution that the photocatalysis methods can give to us. So let me explain a bit this plot. So here you see the number of sources as a function of the flux multiplied by the flux to the second power as a function of the flux. And this is the flux of photons for energies larger than 10 GeV. Here as points, you see the source count distribution of sources into the catalogs. This is a fourth Fermilab catalog. And at some point, this, because of the detection threshold of your catalog, the detection sensitivity, is going down. And then you see those lines that are not affine to the data, but are an independent measurements that we have been obtaining with the photocatalysis method. So in this method, and with the results and the different lines here, just assume different models for the signal and the background coming from the galactic center and from the diffuse emission, we find that there is a population emitting photon fluxes until 1 energy of magnitude and even below with respect to the catalog sensitivity threshold. This means that part of this population, we cannot say all because we can measure only the average properties of the source count distribution in the full region of interest, but part of these sources might be contributing to the galactic center excess. So all in all, those results for us corroborate at least partial stellar origin of the galactic center excess. So there are many prospects starting from here, and I'm going to tell you a bit in the few minutes I have left what we expect if one of the two hypotheses is correct. So if we are seeing really dark matter annihilation into the inner galaxy, at some point, we would expect a consistent signal elsewhere. Long story short, so far, we don't see a consistent signal elsewhere in different probes of indirect dark matter detection, antiprotons, cosmic rays, or gamma rays from other targets. So the region in which we can explain the galactic center excess is actually started to be tested by other independent probes. If, on the other hand, the excess comes from new stars, we can try to invert the reasoning and say, what are the consequences for dark matter? So if the bulk of the galactic center excess flux that I'm seeing is coming from new astrophysics, what is the space left for dark matter? And this is some preliminary results that we have been working on in the past few years, and we hope to publish soon. So in this plot, you see what are our current annihilation cross-section results as a function of the dark matter mass. We have different lines here, so concentrate on the blue line, which is assuming a specific dark matter profile that would explain better the dark matter signal. So in the assumption that what we see at different energies is actually coming from stars, possibly millisecond pulsars, this is the constraints that we can put on a possible dark matter signal into the galactic center. So we see that those constraints compared to other constraints, for example, the ones from dwarf spheroidal galaxies, are much more strong into the 10 to 100 GeV. And they are indeed the potentially strongest in the GeV mass range. So with this paper that we expect to publish in the next few months, the message is that we can possibly, if we are sure enough that the galactic center excess is indeed coming from stars and millisecond pulsars, we can use again the center of our galaxy to put strong constraints on dark matter, in this case WIMPs, but also other models. And finally, a word on the stellar hypothesis. In this work, what we have been doing is not to model the luminosity function of this new stellar population, but assume that can explain spectrally, especially the galactic center excess. But still, the properties of this excess might be unveiling to us a new exciting population of gamma ray emitters, because so far millisecond pulsars are not detected at energies larger than 30 GeVs in gamma rays, and this will be one of the first hints of global contributions of gamma rays coming from millisecond pulsars. There have been some hints in globular clusters that needs to be confirmed, but here definitely the Telecom telescope array is going to help us in the next future to try to understand by looking to the properties of the possible excess that might be present at the energies in which the telescope is going to be sensitive to. We might be able to see and possibly characterize what are the spectral properties of this high energy tail and correlate better those properties to the luminosity function of this new population. And in this line, for sure, advancement in the theoretical modeling of the production of photons in millisecond pulsars and the acceleration and the expected signals are really necessary. A word on other wavelengths. So searches for this bulge millisecond pulsar population contributing to the excess in other wavelengths, specifically in X-rays and in radio, are ongoing. So far, we don't have an evidence for this population, but we expect to have possible new detections with upcoming instruments, for example, with some surveys coming from SKA. And this brings me to my summary. So the summary is again the same as the take-home list that I've been doing at the beginning. And I hope that now you can understand a bit better those phrases. So while searching for indirect Darmstadt signals, we found an excess of GV gamma rays at the Milky Way center. The interpretation is debated, as I tried to explain, but recent results support new astrophysics. And complementary multi-wavelength and messenger probes in the next future will definitely help us deciphering this excess. But in the case in which the excess is coming from new astrophysics, I think that we can rehabilitate the GV gamma rays from Fermilab and from the galaxy center to test dark matter models. Thank you very much for listening, and I'm happy to take questions.
Thank you very much, Silvia. That was really fantastic. Do we have questions? I got a couple while I guess people are thinking. So one is fairly naive
Yeah.
in regarding the dark matter halo. So I mean, I understand there is a density distribution, but is that smooth going out, or like would you expect to trace the baryonic matter in some sense, or how does that
What you
distribute
are
really? Like what?
This is a very recent sort of debate. What is the density distribution of dark matter into the inner galaxy for the Milky Way, but for Milky Way-like galaxies? And as a matter of fact, it's very difficult to resolve the scales that we need in cosmological simulations in order really to characterize what is the morphology of a possible dark matter distribution, and there might be feedbacks, as you possibly are hinting to, within the dark matter and the baryonic components that might distort also the dark matter signal. There have been some recent results in which this seems to be the case, in the sense that with n-body simulations that can simulate dark matter-like objects, you see that in the end, you can obtain also some sort of deformation in the dark matter signal. And this might be letting fall the hypothesis that I've been telling to you before, that the morphology is really is having a discriminating power, but needs to be confirmed. And extracting the properties of dark matter from cosmological simulations for Milky Way-like objects is very difficult. So this is definitely something that you might heard about in the future, because it's one of the lines in which we are going as a community.
Okay. So I see John's hands up, so I'll save my question for later, the second one. So John, go ahead.
Can you guys
Hello.
hear me?
Yep.
Yes.
Okay. Hi, Sylvia. Great, fantastic
Hello.
talk.
Thank
So I guess I was wondering a bit about millisecond pulsars. So I guess we know that there should be at least some millisecond pulses in the galactic center. There can not be no millisecond pulses in the galactic center. So these should give at least a partial explanation for the signal, right? So I was very much intrigued about the work that you showed on slide 35, I think. So the one before that.
Here. Yes.
No, maybe one more. Sorry, the your new paper. Yeah, that's the one.
This one. Yes.
Yeah, this one. Sorry, 34.
Mhm.
Uh, yeah, so I was wondering if you could just elaborate a bit more on that because that seems very intriguing to me, very interesting. I
So
mean, how
this
much
is
space there is left at the end? What's the take?
yes. So the exercise that we are doing with this work is the following. So if we trust the statistical evidences that we are currently obtaining, that the excess is better explained by stars, stellar distributions, possible millisecond pulsars, we can use the inner galaxy as a constraint uh, region of interest, right? Because you say, okay, we don't see this. We don't see that data matter signal. It happens that since it's the region in which we have the expectation for the higher signal, we can indeed um, extract some of the most constraining limits on the presence of dark matter. Of course, here, systematic uncertainties are your enemies because you might tell, well, but you need to vary together the different components in order to understand if they are degenerate. And this is what we have been doing. So in order to explain the inner galaxy gamma rays in the work that I'm showing to you here with preliminary results, what we have been doing is to vary altogether diffuse emission, millisecond pulsar emission, and dark matter. And it's somehow the fit that is choosing to give majority of the photons, according to our models, to the millisecond pulsars with respect to dark matter. And this is the reason why we can obtain such constraining results. Now, the question is, the model that is coming out of this stellar explanation of the galactic center excess is some sort of physically motivated, but is not directly connected to a specific luminosity function. So the next step will be to actually verify if you can explain the observations with a reasonable model for your emission of photons. And this was
Got it.
what I was showing to you here. I hope that now is clear.
Got it. Yeah. Okay. So yeah, I guess how do you exactly do this exercise? You take into take advantage of the fact that these components have slightly different spectra, maybe, and
Exactly. So what we do here is to fix the dark matter spectrum because we're really testing a specific model. We are testing a WIMP that is having 10 GeV annihilating to BB bar. So here let me go here. I was having the flux, exactly. So we are testing really the spectrum because dark matter cannot give you the high energy tape, and it's also having specific
got it.
spectral shape depending on your model. But also we are testing the morphology, and this is what I've been showing to you before. So dark matter spherically symmetric versus a distribution that is made out of the all stars into the stellar bulge. As we were saying before, if at some point you demonstrate that the dark matter distribution is not spherically symmetric anymore at those angular scales, results can change. But to the best of our knowledge at the moment, we don't have such deformations at very high angular scales. So this is the way in which we try to disentangle. The photons go more into the stellar emission template with respect to the dark matter.
Okay. Thank you very much.
You're welcome.
Thank you.
Johanna? Johanna, can you hear us?
I
You're
think
muted.
she's coming.
Okay.
Okay.
So yes, my computer was just
Hello.
lagging. Okay, so I also have a question for you, and this is more like on the status of how you obtain the Fermi data. So what I know about the Fermi data so far is that if you want to obtain like this gamma ray fluxes, you kind of already assume like a template. True. So I'm wondering what you assume to basically obtain those excesses, because I mean, as you already mentioned, I think on one of these slides that it like these templates like have a huge variety, and yes, so they also cause errors, right?
Yeah. So the formula data, they come with a number of counts with respect to position in the sky and energy. So if you extract the data, this is what you obtain, and this is the map that you see. If you want to interpret them and extract the excess, you're right that you need templates. And this is what I've been explaining, I hope, here, that we extract the excess as a remaining photon flux once you model the diffuse emission and the detected sources. It's definitely correct that you have systematic uncertainties in the diffuse emission and in detected sources, but in those 15 years, we have been varying the galactic diffuse emission models in the space of possibilities that we have at the moment. The detected sources, we have been changing their models, we have been masking them, leaving them free to vary, and in all those different attempts, we still find an excess of photons. So at least the fact that there is an excess is not depending on your different templates. We can, I think, say that. Now, the question is, are we missing some new components in those templates? Possibly yes. And at some point, if the excess is coming from new stars, those stars should enter your detected sources or your unresolved source template, right? So what I'm claiming here is that there is something that we don't understand that is leaving to you some residuals that is more significant with respect to your systematic uncertainties somehow. Then the systematic uncertainties of the interpretation are more tricky. And I agree with you that you might say, okay, but if I change the inverse Compton map and I put a new electron density exactly at the center, I might be mimicking this, but what you are telling is that there is still new physics, right? Because the inverse Compton template maps are created according to our best knowledge of the cosmic ray distribution. So I hope that this was clear. No.
So just to make it sure, so for basically obtaining this access, you first just like have the Fermi data and divide them by basically the like the time you look at the certain direction, and then use this raw data to apply like a filter on it. Because like when you have like point sources, what I know there is that you already assume like a spectral model and then fit some parameters to it, but you work the other way around, right?
So this is a technical question. So once you have a photon flux as a function of the position and of the energy, what we do in order to analyze formula data in the majority of the methods that we have been developing is what we call template fitting. So we have different spectral and spatial templates that we try to optimize with normalizations, with variations in order to explain the data. The question on the detected sources is very tricky because you can follow different approaches. You can take as granted the results of the catalogs that they have been doing a lot of work into try to understand the spectrum of the sources, or you can, this is one, you can mask them. So you can mask the region in the sky in which you know that they are detected sources, or you can try to list free some of the parameters. And in many of the works that I've been speaking about, different of those techniques have been investigated.
Okay, thank you. Yes, that was very helpful.
You're welcome.
Are there any more questions? I don't see any hands up, but maybe I can ask my last one.
Right.
So I guess, but I mean, this is my hypothesis that the millisecond particles are thought just because, you know, this is the dominant galactic population for me, right? But now that you have LASSO and other other guys finding pevatrons and things that are not millisecond pulsars, right? Is it possible that you have some other population with a harder spectrum that is doing this excess instead of the millisecond pulsar?
This will be very interesting, but it will be strange that this population is not very evident at the GV in other regions, right? So what you are telling is that, so this is the spectrum, right? What I show here. So you still have the majority of the flux that comes into the GV range. So it will be very interesting if a new population will be showing up at the TV, but is also giving an important contributions at the GV, and we didn't saw this in other regions of the galaxy. Can happen whenever you have a specific source distribution that is only characteristic of the inner galaxy. It might be interesting to see indeed if in the inner galaxy region in LASO or OCData we have some peculiar sources that we cannot explain other ways. This can be definitely an idea. What we know, although from LASO pevatrons, is that the majority of the sources that we are discovering are leptonic, right? So this is kind of also a hint that maybe pulsars and millisecond pulsars might be a good match for what we are seeing.
Okay, cool. Cool. Well, if there are no other questions, then thank you very much, Silvia. That was really fantastic. And we
Thank you
hope
to you
at
for
some point
the time.
you we'll have you here in person as well. So
Who
you can
knows? Who knows?
visit
It would be
Crete.
nice. And if whatever anybody of you would pass by Paris and wants to visit us in our laboratory, please reach out.
Thank you. Thank you. Cool.
Have a nice
So take
afternoon.
care. You too. Bye,
Bye.
everybody.
Bye bye.